Stepping out onto a high ledge with absolutely nothing but open air beneath your feet triggers an immediate primal alarm. But that alarm is quieted by a clever trick of physics. A cantilever is a rigid structural element fixed at only one end. The free end extends into open space, carrying its own weight and anything placed upon it. The architect Frank Lloyd Wright pushed this concept to its artistic limit. By anchoring these thick concrete terraces into a central stone core, he allowed the living spaces of falling water to hover directly over a rushing stream. We use this structural logic to push our footprint past the solid ground, projecting our spaces outward to merge the built environment with the natural world around it. Long before steel and concrete, builders used heavy timber to achieve a similar effect. By extending wooden beams past their supporting stone bases, they created large overhanging upper floors, expanding the usable space above the foundation. The introduction of reinforced concrete allowed these simple wooden outcroppings to evolve. The steel inside the concrete handled the stretching forces, allowing entire load-bearing floor slabs to reach much further into the void. Today, modern urban developments stack these elements aggressively. Designers can stagger and extrude multiple box-like residential balconies, expanding the square footage of the building without needing a larger plot of land. Mastering the cantilever allows a building to capture volume where the ground cannot, turning empty air into functional, inhabitable square footage. To hold up those floating rooms, the cantilever acts like a rigid seesaw. For every foot a beam extends outward, it must extend deep inside the building's core, using the massive weight of the structure itself as a counterweight to hold the free end steady. Within the projecting beam itself, an intense, invisible battle takes place. As gravity pulls down on the unsupported end, the top half of the beam is being violently pulled apart. Engineers call this pulling force tension. The steel reinforcement laid along the top edge is placed there specifically to hold those stretching fibers together. At the exact same time, the dynamics are reversed along the bottom edge. Here, the weight of the overhang is driving the material inward, crushing it together. This is compression. Concrete excels at handling crushing pressure, while the steel above handles the stretching. A cantilever maintains its position only by securing a perfect silent equilibrium between these two forces within its anchored root. When engineers applied these principles to the Industrial Revolution, the scale expanded exponentially. Massive steel trusses, like those on the Forth Bridge in Scotland, were designed to carry the immense weight of railway systems over deep water. Their primary advantage was logistical. Because a cantilever supports itself from a fixed anchor, builders could construct the bridge outward piece by piece, completely eliminating the need to build temporary scaffolding up from the dangerous waters below. The approach is to build two independent cantilever arms from opposite banks. They stretch out across the vast obstacle, unsupported from underneath, until they finally connect and lock together in the center. To handle the moving weight of massive freight trains, these structures rely on incredible density. The deep, webbed geometric design of the steel framework provides the extreme rigidity necessary to keep the span from bending. By harnessing tension and compression on a massive scale, humanity bridged deep rivers and gorges without having to fight the massive geography beneath the water. But this structural logic functions just as effectively at the micrometer scale. If we travel through the crystalline lattice of that bridge steel, we find ourselves in a highly advanced laboratory. Here, the cantilever has been miniaturized. Instead of thousands of tons of riveted steel, we have a micro-machined sliver of silicon. This is the heart of an atomic force microscope, a tool that uses a microscopic cantilever to map the surface features of materials at atomic resolution. At this scale, the beam functions as a sensory appendage. It translates the topography of atoms into physical movement that the microscope can measure. In tapping mode, the microscope drives the tiny cantilever to rapidly vibrate up and down, oscillating near its natural resonance frequency. On the unsupported end of the beam sits an incredibly sharp tip. As the instrument lowers this tip into close proximity with a material sample, it encounters atomic forces. Attractive and repulsive interactions between the tip and the sample physically push and pull on the beam. As the cantilever scans across the microscopic bumps and dips, these forces directly alter the amplitude of its vibration. To read these tiny changes, a laser is bounced off the back of the bending beam and into a split photodetector. Even the slightest atomic repulsion causes the beam to flex, shifting the angle of the reflected light. By converting physical resistance into measurable light deflection, the cantilever transforms a mechanical touch into a highly precise atomic eye. This technique has allowed scientists to map and analyze everything from novel energy storage materials to living cells and biomolecules. Whether it's a railway bridge or a silicon probe, the core mechanic is constant. Both rely on the relationship between a fixed support and the flexibility of a beam to resolve an external force into a measurable deflection. The same mastery of tension, compression, and a single fixed anchor that suspends a balcony over a canyon also provides the mechanical bridge to reach out and touch individual atoms.